Now in this video, we're going to create linear programming problems to solve a general finite, say m by n, game, the type we've been talking about here in part 2. Remember, when we're trying to find minimax strategies for the game, player 1 would like to maximize this quantity. This quantity is this minimum for j going from 1 to n of this sum from I equals 1 to m of p sub I times aij. I'll remind you what this sum was. This sum says the following. If player 1 chooses a mixed strategy p, so you have this strategy vector p, which is p1 through pm, giving probabilities for player 1 to choose each of the different columns. So if player 1 announces, I'm going to play p, this sum tells player 2's expected return if player 2 plays column j, and player 2 wants to keep that as small as possible, and so player 2 would like to minimize over all the columns j equals 1 to n this expected return given player 1's strategy. So this is kind of, this minimum would occur if player 2 plays the best column choice or best response column to player 1's choice of p. Player 1 would now like to maximize this, make this minimum expected return as large as possible, because then player 1 can guarantee at least that amount. And that's what we've been calling the lower value of the game, v lower bar. So the goal is to maximize this function. And you'll see this is just a, well, it's a strange thing. Right now it's not written as a linear function because it has this minimum in here. But that's the thing player 1 wants to maximize. Now, I'll remind you that in order to have this all make sense, for player 1, this column vector p has to be a probability vector, so the sum p1 plus p2 up to pm has to be 1, and of course all of these probabilities have to be greater than or equal to 0. It's not, as I said, already a linear programming problem because this isn't just a linear inequality. This has this weird minimizing function in it. We can turn it into a linear programming problem by creating a new variable, which we'll call little v here. And now we'll say we want to maximize this, this function v. Think of that as a linear function of one variable. Now, of course, we have m plus 1 variables. We have all the p's, and we have the new variable v. And our objective function is just this single variable v. We want to maximize that subject to the conditions that v is less than or equal to this sum of pi times ai1. This represents player 2 choosing column 1. V will be less than or equal to the sum from I equals 1 to m of pi ai2. The same thing for pi ai3, all the way up to v less than or equal to the sum from I equals 1 to m of pi ain, plus the normalizing conditions we had before, that the sum of the p's is 1, and p1, p2 up to pm all have to be greater than or equal to 0, since they represent probabilities. Now, what are we doing here? Well, this new variable v should be less than or equal to all of these. Player 1 wants to maximize the minimum value of these. Well, if v is less than or equal to all of these, v has to be less than or equal to the minimum of all of these n different things here, which is exactly what this quantity is. So these n linear inequalities, if v satisfies all of them, that says v is less than or equal to this exact thing, the minimum of this sum. And of course, the objective function is v, and player 1 wants to maximize this number v, which is less than or equal to that minimum. That will happen when that minimum, of course, is largest, and when v is equal to that minimum. So this effectively creates exactly the situation that we like. This v will be the thing that maximizes this minimum. This v, when we solve the problem, v will be exactly this thing we call the lower value of the game. Now, you might look at this and say, is this really exactly a linear programming problem? We have an objective function. We have these variables v and the p1 through pm. Here we have a bunch of linear inequalities. Here we have an equation. Can we do that? Well, yes, it's always okay to do that because you can always think of this equation as two more linear inequalities. You can think of that as P1 plus P2 up to Pm is less than or equal to 1. And a similar thing where P1 plus P2 up to Pm is greater than or equal to 1. Of course, this one has the wrong type of inequality, so you can just replace this by multiplying both sides by -1, and you would get minus P1 minus P2 minus Pm less than or equal to -1. So now if we include these two in place of that one, we really have an honest-to-goodness linear programming problem, and it's something we can solve, and it'll give us this lower value of the game. How do things look from player 2's perspective? Well, player 2 wants to maximize this other sum. This sum, player 2 wants to maximize. I'm sorry, let me start again. Player 2 wants to minimize this thing, which is the maximum of the sum j equals 1 to n of aij times qj. Why is that? Well, remember, if player 2 says, I'm going to play strategy q, which is q1 through qn, choosing column 1 with probability q1 up through column n with probability qn, then for each different row player 1 could play, this will be the return, and player 1 will want to pick the biggest one, of course, so we look at the maximum return that player 1 can get. That will be player 1's best response return for player 2's play of strategy q, and player 2 will know this, so player 2 wants to make this the smallest possible. Player 2 wants to minimize this maximum over I equals 1 to m of this sum. Well, just as before, we need the sum of the q's to be 1 and all the q's to be greater than or equal to 0. Since q is a probability vector, how do we turn this thing into a linear programming problem? Well, just as before, we create a new variable. This time, let's say we call it w. And now we can ask to minimize this w. This will be our new objective function. And how do we minimize this w? Well, I'm sorry, how do we minimize this quantity here? And why is that the same as minimizing the w? Well, we're going to put these constraints on w. W will have to be greater than the sum from j equals 1 to n of a1j qj. This is exactly that expected return. If player 1 plays row 1, then you'll have the same thing with player 1 plays row 2, player 1 plays row 3, up to player 1 playing row m. If w is greater than or equal to all of these, w will be greater than or equal to this maximum here. And if we find the smallest w where that's true, we'll find the smallest w greater than or equal to that maximum, which will be exactly that maximum. And again, we put in these two other equations, just saying q is a valid probability vector, and just like before, it's okay to have this equality here because you could replace that with two inequalities. So for player 2 needs to find the find the minimum w subject to all of these constraints. And what will player 2 have done then? Well, this minimum for w will be what we've been calling the upper value of the game. And player 2 will be able to force a situation where player 2 does no worse than this upper value, the upper bar, that's this minimum w. Now here's the neat thing. This is going to be exactly the dual of the problem player 1 faced. Player 1's problem to find the lower value of the game and player 2's problem to find the upper value of the game are exactly duals in linear programming. And we'll talk a little bit more about this in the subsequent video lectures, and it's in the book. But as dual problems, they have to have the exact same solution. And that's what the minimax theorem is all about. One had solution which was the lower value of the game, the previous one. This one has solution which is the upper value of the game. Those solutions have to be the same, which tells you the upper value of the game has to equal the lower value of the game. And then these probability vectors, the p's for player 1, the q's here for player 2, will be exactly optimal strategies because they'll be probability vectors where each player, player 1 for the p's, player 2 for the q's, plays a mixed strategy with these probability vectors. Each one can guarantee no worse than now this common value of the game. Now that would all be good. I want to show you just one simplification we can make for both players to make it more of an easy to deal with linear programming problem. This will be very straightforward. For this simplification, we're going to assume the value of the game is a positive number. And remember, that's not an unreasonable assumption. If you happen to have a game whose value is negative, you can just add a constant to every entry, change the matrix by doing that, and the game will play the same. It will have the same optimal strategies, and the value will just be increased by that number. So you can just do that, solve that game, and then at the end, remove that constant. So that's not a serious thing to worry about. Once we've assured ourselves that the value of the game is positive, then we take these p's, say this is from player 1's perspective. Remember, player 1 is looking for a mixed strategy, that probability vector p, which is the column vector p1, p2 through pm, and we're going to create new variables x1, x2 through xm, where x sub I is just p sub I divided by this value v, and we'll do that for each one through m. Then instead of writing p1 plus p2 to pm is 1, just dividing everything by v, we get x1 plus x2 up to xm is 1 over v. Now, maximizing this number v will be the same as minimizing the x's, our new objective function, x1 plus x2 up to xm. So we're going to totally get rid of the old variables, the p's and the v, and we'll just have this new objective function, x1 plus x2 up to xm, which now we want to minimize. And what are the constraints? Well, our constraints now, remember, we used to have that these sums were greater than or equal to v. We divide these sums with a p sub I here, we're greater than or equal to a v. Dividing by v, we'll get 1 is less than or equal to this sum from I equals 1 to m of x sub I ai1. The same thing, 1 is less than or equal to the sum of xi ai2, all the way up to 1 is less than or equal to the sum of xi ain. And now instead of having all the p's be positive, since we've already assumed v is positive, we just have all the x's positive. This becomes our much simpler presentation of a linear programming problem where this is our objective function, just the sum of the m variables, x1 through xm. Our linear inequalities, our constraints are here, and just our normalization of the variables is here. Once we solve this linear programming problem for the x's, we can recover the value of the game. V is just 1 over this sum of the x's. Why? Because the sum of the x's would be the sum of the p's, which is 1, divided by v. So 1 over that will be v itself. And of course, we can just multiply both sides of this equation here by v, and we get each p sub I is v times x sub I. So we find the maximum value of the objective function. We find the x's which produce that maximum value, and that will tell us our optimal strategy, the vector probability vector v, and this value of the game v, which is 1 over that minimum sum of the objective, the minimum value of the objective function. I might have said maximum before. We want to minimize this objective function, because maximizing v before was like minimizing this new function. So this is now a very nicely simplified linear programming problem in just these m variables, x1 through xm. Doing the exact same thing from player 2's perspective, instead of this new variable w that we added, as long as w is positive, we divide each of the each of the q's, in the probability vector for player 2, we divide each one by w and create new variables y, y1, y2 up to yn. And just like before, we have the sum y1 plus y2 up to yn will now be 1 over w if the y's are defined like this. finding the minimum for W is then just like finding the maximum for this new objective function, y1 through yn, and we get these linear inequalities, which used to have, say, a q sub j there and w there, dividing by w. They'll all be of the form sum from j equals 1 to n of a1 j yj less than or equal 1. That's for row 1. And we keep doing that all the way up to row m, the sum of a sub mj yj less than or equal 1. And our normalization there too. So this is our new objective function. These are our new constraints and our regular normalization there. Once we find the maximum value this time for our objective function, we can recover, again, w is 1 over the sum of the y's, and the probability vector q, which will be the optimal strategy for player 2, q sub j, each q sub j will be w times the corresponding value for y sub j that led to the maximum of our new objective function. And the way we formulated here, it's very easy to see that just like in the example I showed you in the previous video lecture, this is actually the dual problem of this one here. In this problem, we have the variables x1 through xm. We have these linear inequalities. If you write those out in a table, you'll see that reading the table the other direction, that leads exactly to this dual problem. Now, how are we going to solve both the original problem and the dual problem? Well, it turns out there's an algorithm for solving both the original problem and the dual problem, and we really do want to solve both. We would only need to solve one to find the value of the game, but if we want to find the value and optimal strategies for both players, we want to solve both. It turns out there's a version of the simplex algorithm, the dual simplex algorithm, that will solve both the original problem and the dual problem simultaneously, which is really amazing. They have the same value, so of course you'll get the same value for v and w, and that will be the value of the game. And once you find all of your values for the x's and the y's, you can easily compute the p's and the q's, as we've already seen. So we'll talk a little bit about that, though we're not going to get into every detail of how the simplex algorithm works. Remember, if one were to actually graph this, for the original problem in an m-dimensional space, for this dual problem in an n-dimensional space, to maximize the objective function, that maximum will have to occur at one of the vertices of the allowable simplex. If you look at the region which satisfies all the constraints, it's some very strange looking simplex in these higher dimensional spaces. You look at all of these vertices, the maximum will have to occur at one of them, or the minimum for the previous problem, the maximum here for this problem. And one way to do that might be to check every vertex, but that's horribly inefficient because there are just way too many if m and n are big. So the simplex method is designed to give you an algorithmic way of moving kind of from vertex to vertex towards the correct one, which allows you to maximize this objective function, minimize the other one, and find, in this case, the value of the game and the optimal strategy. So we'll talk more about that later.